going to be talking about the correlated worldline theory. We've had two talks, Brigitte and Philip, already that did quite a nice job of it, and so I'm not going to linger too much on the introduction. I'm going to get into a bit more of a different aspect of it and maybe clarify some details because there were some questions I've received throughout the week. What I'll be talking about is largely based on things that have been done already with Philip when I was a student, and some things that are ongoing with Yanbai Chen and Philip right now at Caltech. And I apologize, but I didn't include the acknowledgements of Brigitte and Kai over at Berkeley on this slide. So what we're trying to do is come up with a model where we're going to allow quantum mechanics to break down, and we want to keep as much about general relativity as possible. The last question we just had illustrated the fact that when you try to break the rules of quantum mechanics, you already get kind of confused when you start asking questions about the non-relativistic limit and promoting it upwards. And so one of the goals of this CWL theory is to actually have general covariance just built in from the start. Another goal that was put into this is there was a desire to have no external noise acting on the system, as some people might be familiar with in the Penrose model and other models of this type. The external noise can lead to a heating effect, which clearly violates conservation of stress energy, and it kind of precludes the idea of general covariance, unless you're very clever, as some people are, but we tried to just get rid of it from the outset. And eventually, and I'm not going to spend much time at all talking about point 3, but one of the goals originally with this CWL theory was to abandon various quantum mechanical structures, such as a projection postulate, et cetera, and have something like a dynamical collapse built within the theory. As you might have seen already in all the talks, we start with the conventional quantum mechanical path integral. We have all these different paths for the system. You sum over them, that is the superposition principle. And so if you'd like to violate quantum mechanics, you have to modify this sum to include correlations between the different paths. And so it's now no longer just a simple sum over individual paths. I remind everybody that this is meant to represent different quantum paths of a single system. So this is a point particle, for example, and its different paths are correlated. And the simple intuition is that for an electron, the gravitational interactions between the various paths will be negligible and you'll have quantum mechanics. But for a bowling ball or maybe even Earth, the gravitational interaction is now sufficient that the paths would collapse and you get something like a single classical trajectory. So let me put up a big formula and have everyone stare at it for a moment while I talk about different aspects of it that will hopefully clarify some of the questions that we've been asked. So if I used a variable phi here, I could have used the variable q, I just have some matter system. In fact, I probably should have used q to keep the discussion simple. So let's pretend this is just a point particle. If I want to describe multiple paths interacting with one another for that point particle, I can't use just the single integral because that has manifest linearity. And so the formalism that was settled on by Philip and Andrei Bervinsky was to use this kind of product structure, or to replicate the structure of the path integrals, where you now have some large number, n, copies of my matter system, and they all interact with each other via gravitation. And I'd like to point out something about this object that I've called K. I hesitate to call it a propagator because that can confuse some people, so let's just say it's a mathematical function, and I'll tell you what it means in a moment. But as far as something that we can be computing and talking about, aside from these square brackets, everything inside here just looks like a conventional path integral approach to quantum gravity. There's nothing kind of unusual going on. It's all in the interpretation of these many different fields, trying to interpret them as the propagation of a single object. It's all in that step when things get a little funny. And that's what these square brackets in the 1 over nth root, that's where that comes in. One thing I'd like to point out is if I have n copies of my matter action up here in some sort of semi-classical limit where I'm not really worried about the path integral, then I have n copies of my matter stress tensor. And so to recover proper conventional classical GR coupled to matter, I need this factor of n sitting in front of my gravitational action so that I have n times Einstein-Hilbert on one, or sorry, n times the Einstein tensor on one side and n times the stress tensor on the other side of my classical equation. And so manifestly, in this form, you know that you have the correct classical limit of your theory. Additionally, this 1 over n structure that appears here, which is quite odd, is necessary because if I wanted to turn off gravitation and have correspondence with conventional quantum theory, I would set G to 0, kill this term off, but now I have n copies of my conventional quantum system, and so I need to do something about that. That's taken care of by this nth root. Now, I was a little ambiguous about what this K means. This formula is a little bit schematic. It's meant to resemble a propagator, but really what one should be doing is compute this quantity, take its modulus square, then take this nth root, and now we're going to say that that is your quantum probability, or your CWL probability. Something else I'd like to point out is everything inside these square brackets. Like I said, it's just a conventional quantum gravity theory. We're going to assume that this is the standard low energy EFT. I'm not going to bother with ambiguous questions about the definition of this measure. I'm going to do everything in a more of a conventional sense. This is something that's just been studied before in the literature. The interpretation is, of course, different, but this mathematically is something that's been studied in the late 70s and early 80s, and it's really just large N quantum gravity. To illustrate that, there is actually two kind of separate approaches to this, and I'm going to do a little formal aside to the approaches that resonate with the things that have been in the literature before, and then I'm going to step into things that are present for, that are relevant for present experiments. So if one looks at, say, field theory in this CWL formalism, we can compute correlation functions by writing down a generating functional and differentiating in all the standard ways. And because of by construction, we know that when G Newton goes to 0, this recovers conventional correlation functions, and so one would hope that we can compute things perturbatively away and see CWL correlations in this structure. And something quite interesting happens. Because we're going to be taking n to infinity, and just by basic combinatorics, when you look at the connected diagrams in this expansion, you'll see that the fastest a diagram can grow with n is linear, and then everything else is sublinear in n. And as n goes to infinity, you throw away a huge amount of your diagrams. And if the pattern isn't obvious from what I've drawn here, any diagram which has a graviton running in a loop gets thrown away. And one can see this as a pattern here, but one can also just prove that systematically. Now, this isn't original to us. We actually discovered it a little independently because we weren't looking in the right place in the literature, but this was already noted, as I mentioned, by Tomboulis, Smolin, and others. Now, something else that's interesting about this model, and as I said, I'll get back to more concrete experimental realizations in a moment, is that it's actually renormalizable. And while modern day approaches to quantum gravity don't focus so much on renormalizability, it's kind of an interesting thing to note. And it's a simple fact that you can compute exact correlation functions. Say if I have a free scalar field and I want to compute its 4-point function, the only thing that happens is this graviton propagator gets renormalized by scalar bubbles. Now, I'm assuming that the scalar field otherwise doesn't have self-interaction, so this is something I compute. And we know that gravitation won't generate self-interactions because I've thrown out all of my graviton loops. And so this is just something you can go ahead and compute. And it has a divergence, as you might expect, and that divergence is killed off by the addition of a higher curvature term. But because there are no graviton loops, that higher curvature term does not feed back in and generate further divergences. Now, people in the past looked at such theories, and they thought, that's quite interesting. They have asymptotic freedom. It flows to something which is actually quite different than GR when you go to high energies. But these effective field theories, which are truncated at quadratic order in derivatives, quartic order in derivatives, they're unhealthy, they're sick. But I would like to appeal to authority, or at least step back and recommend that people look at John Donohue's recent papers on this topic, because he's really advocating that people need to be rethinking this point, and I'll leave it at that. So away from the field theory stuff, that was more to point out an interesting connection between CWL and things that people have looked at in the past. Let's focus on propagators. So not correlation functions in some field theory, just evolution of a state from one configuration to another. And what's interesting is that you can still use this large N approximation to say something about the mathematical structure of the theory. And basically, it just affords you the ability to just integrate out the gravitational field. It sits right on the saddle, and subleading corrections are order 1 over n, and n's taken to infinity. And so what that means is that you are left over all of that mess with n fields and a gravity integral to do. You're left over with a single matter integral to do, where your matter lives on this self-consistently determined metric I called g bar here, which satisfies something that looks like an Einstein equation, although the right-hand side is a little bit strange. I refer to this as an in-out semi-classical Einstein equation, and formally speaking, it is just different and has different properties than the standard semi-classical Einstein equation. I'll illustrate that point here a little bit more, because as many people in this room know, and as I was taught by Bill Unruh, in standard semi-classical gravity, you have a complete inconsistency when it comes to quantum measurements. If I have some state psi, which sources my gravitational field, and then I measure the state, say it projects onto some new state, lambda, I'm now going to have a quantum jump. What that causes then is a discontinuous and non-local change in my stress energy tensor, and that will cause a discontinuous and non-local change in my Einstein tensor, and this is completely incompatible with the properties an Einstein tensor is meant to have. Now, I can't prove the consistency in this slide of the in-out semi-classical approach, but I can at least provide some evidence that it doesn't immediately suffer the same problem. So this is a little bit lengthy, but in short, if I have some propagation from some state phi1 to some state phi2, and I want to say that there was a measurement that was performed in the intermediate in between there, then I have the formula previously gets modified to something where I have a time-ordered product of the projection operator onto the state that I measure with the stress tensor. And without going into much detail, at least in simple examples, it's actually quite clear that this is not discontinuous. And it's simply because as I approach this lambda with my t, it looks like lambda as I get close to it, and then as I get away from it, it still looks like lambda, and there isn't just a discontinuity across lambda. Now, one would also like to prove something like the stress tensor being conserved. That is obviously important as well, and that just can't be proven in general from this formula. However, there was a statement in our paper with Andrei Barvinsky in the field theory approach to CWL where we demonstrated that there was a gauge independence of our correlation functions, which is a formal way of saying that stress energy is conserved, at least at the level of that model. So let me now get on to things which are probably more interesting to some of the people in this audience who want to get things done, as Philip said. So this is great. We have a model. We have a bunch of formal structure. What does it actually say? Will I look for this? Is it already ruled out? The simplest thing you can do is to just take two paths out of this collection and just estimate the scale at which this is appropriate. It's literally just a hydrogen atom problem, and you can port over all the scales you might want from hydrogen and just plug in appropriate gravitational constants. And something I'll note is that the gravitational energy, the scale associated in this point particle limit, the scale associated with a particle of mass m0 actually increases very rapidly as the power of m to the fifth. And so for something like a virus, which has 10 to the 9 AMU mass, this is completely negligible. That's way too low of an energy to be seen. But already just a few orders of magnitude above that, say at a bacteria or 10 to the 13 AMU, we are at actually a rather appreciable energy scale. Now, this was a childlike approximation, but I just wanted to illustrate that these scales in between this 10 to the 9 and 10 to the 13 AMU are completely physically relevant, and so it warrants doing a proper estimate. To communicate that proper estimate, I'll actually refer to some things that Brigitte had mentioned and that Jan Bay actually just talked about. One has to take an actual model of a physical system because obviously there are not point particles in nature with an incredibly high mass like I just mentioned. And so what this cartoon on the left is meant to represent are two paths or two replicas for some extended body, let's say an amorphous blob of silica. And what these chocolate chips in the cookie are meant to represent are the length scales over which the little ions will actually fluctuate, because obviously ions in the material are fluctuating. And that actually is an essential length scale. For a common material, this might be 3 picometers. This plot on the right is basically the effective interpath CWL potential energy, gravitational potential energy. Now, when the objects are well separated, you recover a 1 over r potential. I should hasten to say that I have rescaled all of the things here. There are no tick marks, just to illustrate the different features that one sees in this plot. It doesn't exactly look like this. But when the objects are well separated, you have a 1 over r potential, as you must have. There's an intermediate regime where some of these dark blue circles start feeling the mean density of the entire other object, and that's when you start to regularize that 1 over r into something smoother. And then there's a final regime where those different replicas are sitting basically right on top of one another, and you have a strong overlap between all of these dark blue circles and their counterparts. And in that regime, you get this extra little spike, referred to as the spike potential. Brigitte had mentioned this as well. Now, as Jan Bay pointed out, when you look at models like this, you have a parameter that comes out, or a scale that comes out, which is basically the square root of the product of g Newton times some density appropriate to the problem. Now, I think Yanbei had it on his slide. It was about the microhertz regime when you're in this intermediate scale, whereas when you're in the spike, the appropriate density is the mass of a given ion in this material divided by the volume over which it's fluctuating. And that's a much higher density, and we can get up to, say, 25 millihertz for silica. Now, I have some crude estimates on here pulled from experimental papers, and I am in no way an experimentalist, and Marcus has corrected me many times when I've pointed some scales out. But very roughly speaking, if one looks at some of his old papers involving optically trapped nanoparticles, they would be in the kilohertz regime, and that's just much, much too fast to see this. Although, I won't speak for him, I've been corrected. They can do much better than this, and they can dial things into the appropriate regimes. Another question that was raised by Bill Unruh is, well, LIGO's probably already ruled this out. Not really a question, more of a statement, but we wanted to address that. And it seems that even LIGO is just too fast to see this. And in a following slide, I'll point out another reason why LIGO probably wouldn't have seen this effect. One place which is quite promising, and it's not the only place, but one place that is quite promising is in torsion pendula, because the resonant frequencies, the mechanical resonant frequencies in these systems are just incredibly slow, and they are in the millihertz regime, but I won't speak much more on that. With all of this being said, one might estimate what mass scale of object should I be using, should I be looking for, and I won't bother you with the details, but it's clear from the shape of that effective potential that you might want the width of your wave function to be sufficiently narrow that the particle and its replica are within that spike well. That's when the gradient of the potential is strongest. This isn't a requirement for seeing a CWL effect, but one might expect that this is kind of a dominant region. And if you do this estimate, it's quite simple. It's kind of elementary dimensional analysis. You can see that you get the strongest effect when your mass is about epsilon times this scale here, 10 to the 16 AMU, where epsilon is a dimensionless CWL coupling constant. This omega spike is that 25 millihertz that I mentioned a moment ago, and this lowercase omega is the mechanical frequency scale of your experiment. So one has some freedom in dialing epsilon downwards, but this is roughly speaking the scale one has in mind. And I'll mention that this is a little bit larger than current experiments, but if I'm not wrong, this seems like it's achievable in the non-infinite future. Very optimistic. Now, has LIGO seen this? Another way of saying this is, if I just set down the most straightforward macroscopic quantum experiment that I can try and set forward, what will I see? And there's actually something I think is actually a feature of this CWL theory. I think it's rather cute, that in the simplest situations that you can set up, you actually don't see a signature. So if I do linear measurements, so I'm just measuring x or I'm measuring p on a quantum particle, and I have a Gaussian state, the easiest thing I can set up, I don't get a signature. And it's actually, this formula might be a little longer than it needs to be, but the idea is simple. If I have many such replicas, I have many wave functions for those replicas. If it's Gaussian, I need to basically take the product of all those Gaussians. But when I do that, the quadratic form that appears inside the argument of my exponential literally just separates off into a bunch of center of mass stuff and a bunch of relative stuff. And we know that these path interactions are all going to live in the relative coordinates. And it turns out that the things you're interested in measuring, like position and momentum, get stuck in the center of mass coordinates. And so all of the CWL effects literally factor out. And so what one has to do is consider a more interesting scenario. So that means that it can't just be a particle in a simple harmonic well, or it needs to be a state, which is a non-Gaussian state prepared in that harmonic well, or perhaps something even more non-trivial. So all of the talks in this session ahead of me actually explain this, and so I'm not going to spend much time on this. But these gravity-mediated entanglement experiments are precisely of the right type to generate a non-Gaussian, non-trivial quantum state. And so I'll just illustrate what I have in this picture. The bottom half can be considered that of a single particle that I'm going to try and use to create as a source to create a quantum superposition of spacetimes. And so I'll send it through a Stern-Gerlach or whatever. and it'll be in a superposition and propagate for some time. And this probe particle up here will also be prepared in a superposition, and it will try to feel the effects of that superposed spacetime. And in the conventional low-energy EFT approach, as we've just seen, one actually develops entanglement between these two particles as mediated by the gravitational field. And that is, as we've just seen, it's not conclusive proof that spacetime is quantized, but it says something about the low-energy EFT that we expect to see in that model. Something that's noteworthy is that CWL theory actually predicts no entanglement between these particles. And so in principle, if this experiment could be done, it could rule out the CWL theory. Another thing that I will talk about, and Bay just mentioned, and I think people this afternoon might mention some more, is a cavity quantum optomechanics experiment. This is my rather crude demonstration of what cavity optomechanics is, and it's at the level that I understand it, and hopefully it's useful for some people in the crowd who actually aren't familiar with it. And it's really quite simple. In this model, or in this physical situation, you have a cavity with, say, a moving wall, a mirror attached to a spring, and there's some radiation pressure because it's a cavity. I can build it up by firing lasers into there. Now, the energy of the cavity modes depends on the size of my system, if I vary that adiabatically. And so, to linear order, I get some coupling to the position of the mirror, x, which is b plus b dagger, the creation annihilation operators for excitations of that mirror. I should mention all of this is in the context of conventional quantum mechanics. I have done no CWL things yet. If I have a strong laser pulse, I can linearize the product AA dagger, and I can get this bilinear coupling where this alpha is an experimental control parameter describing the pulse that I've fired into my system. A and A dagger are the creation and annihilation operators for my cavity mode, and B and B dagger are, as I mentioned, creation and annihilation operators for my physical mechanical excitations. Now, what this situation affords you is quite nice based on basically the profile and the frequencies that I build into this alpha of t. I can engineer all kinds of interactions between the two systems, and in real-world applications by real-world experimentalists, do much more sophisticated things than that. But for what I'm going to say, we only need really the simplest situation, and I just point out that you can engineer a coupling between A dagger and B plus B dagger and A. And so what that means, for people who are not familiar with the field, is that one can literally engineer a swap gate between these two quantum systems. Experimentalists have incredible control over photon states, and they can build single photon states or multi-photon states, and they can send them into the cavity. And that's represented by this little circle here, saying I can just go ahead and create a cavity mode. And this is not a Gaussian state, this is a Fock state. I can then do an operation, which is a swap operation. I've convinced you that that is something that can be done. And so I can create my cavity excitation, swap it, so I have now a non-Gaussian Fock state for my mechanical oscillator, let it propagate for some time, and then just swap it back. And assuming I'm in a regime where there's no decoherence and everything's completely under control, we expect that I will find in my out state nothing in the oscillator and one cavity mode, illustrated by these elegant formulae here. Now, in the CWL theory, the situation has changed. This simple operator formalism, x is equal to b plus b dagger, has to get promoted now to a path integral with all these interacting paths. There's a complication in the formalism, but things are different. How that manifests is in two places, really, that matter, preceding the swap and then in between the swaps. One might think that the dominant effect would be in between the swaps when I've actually engineered some kind of non-trivial state of my quantum system, but that turns out to be subleading to the effect of the CWL before the swap. And so let me comment on what that means, what's happening here. To prepare my system, which I assumed was originally just the vacuum of both systems, the state that was the vacuum of both systems, I would do some kind of cooling process and cooling and cooling and cooling. But because of all the interactions between the various paths for my CWL oscillator, the state that I get, or at least the functional form within the CWL language that resembles a quantum state, simply is different than in plain quantum mechanics. And so when I go ahead and I hit the system with this first swap that I thought was the correct swap gate, it's just not actually the correct swap gate. There's an error. And that error is determined by this epsilon, which I had mentioned on the previous slide, is this dimensionless CWL coupling constant. And so one can go ahead and run this experiment and look for deviations from unit return probability in your cavity mode. I should mention the formulae on here are for a single photon excitation, and Marcus has told me that people could do much better than that, and so there might be a scaling factor in front of this that enhances the effect, but that hasn't been worked out yet. To mention what goes into this formula, it's the coupling constant, just E. G naught here is the coupling constant between the two oscillators, and then this integrated pulse profile shows up. And so the harder I do this, the more strongly I'll see the deviation. So that's it. I think I'm going to be a little faster than I expected, which is totally fine. In conclusion, we see that the CWL theory is conventional quantum theory when I take G to 0 by construction. It's classical GR coupled to matter when I take H bar to 0 by construction. And the interpretation is actually that kind of an in-out semi-classical theory, or at least mathematically that's what it seems to look like. I shouldn't use the word interpretation. Things that I would say it features are interesting connections with asymptotic safety, and I would also refer to the fact that there's no signatures in the more classical quantum states. I'd call that a feature as well. And as I just mentioned, the proposed tests are low-frequency macroscopic quantum optomechanical experiments and gravitational entanglement generation experiments. Thank you.
Excellent. Thank you very much, Jordi. The floor is open now for general discussions. Of course, ideally we start with some for Jordi, and then, but please be free also to pose questions to everyone from this morning's session.
So I have a general question also to Philip. When you are writing in-out matrix element in the right-hand side of the Einstein equation, why you are sure that it's not complex number?
It is in general. You're absolutely right.
Yes, but then you are considering complexified gravity?
That's absolutely right. And
but
I
then if you are doing
what complex metrics look
yeah,
like, but as a mathematical result, that is what we get.
But then, if you have complexified gravity, what kind of gravity it is? It's like Einstein, Strauss, or whatsoever. I mean, this Hermitian gravity, what is this?
I don't have a good answer for you yet. We haven't really worked through those details.
And then second thing, actually, because in linearized level also, if you would consider these things, then there will be a complex part of the metric, which at linearized level will be something like Karl-Paramon field. You see this B mu nu, antisymmetric. But why it's better than to consider in matrix elements?
I would say the in matrix elements just did not come out of this computation. That was, the in-out wasn't an input. That is what we got from doing the path integral and from finding the saddle point equation.
Yeah, I know.
I should mention, I wanted to clarify, when the matter integral, when it has a single dominant saddle, so it looks relatively classical, then you can just go ahead and evaluate that stress tensor, that in-out stress tensor, and it is real. And it is the semi-classical stress tensor that you expect to see. It's only for quantum situations where you have multiple dominant saddles or no dominant saddles that you get this complexification. And I don't know the interpretation.
No, complexification you are always getting for in-out matrix elements because it's not expectation value, in fact.
It can be real.
Andrei Barvinsky knows it quite well. We were writing even with him some papers, okay, on this thing. And then, of course, in matrix element, it's much more headache than in-out matrix element. But as I said, you are getting complexified gravity. It's not just on macroscopical scale. You are getting, when you are writing Einstein equation, you are getting complex metric.
Yeah. I agree with that.
Let's briefly stay ad hoc here. So Renata will be next, but Philip will wants to comment directly.
In answer to Slava, let me just repeat essentially what Jordan said. If we're dealing with situations where quantum effects are important, and he's already pointed out the mass scale where they're important, then we have what you want to call complexified gravity, and that's absolutely right. But in situations where you're dealing with astrophysical objects, it's simply not relevant because the the interaction between the paths is so strong that it just looks like classical GR. So you have to understand here, the predictions are different for the mass scales that we're talking about, but not for astrophysical objects. So it is not complexified gravity on the astrophysical scale.
But what you want to do is just a complete change of the gravity theory on the microscopic scale.
Well, you already knew that. That's what quantum mechanics is.
No, but, okay, really, but go in the perfect universe, right? Then,
there you're right. It predicts different things for the beginning of the universe. And as I said to you before, do not extrapolate quantum mechanics to the cosmological scale without a good reason.
Okay, so it should work, Renate. Mic one.
Am I on? Yes, very good. So a somewhat related question. So you wrote down the fundamental expressions from which you start. You made the comparison. You said, oh, then we discovered, it has been done before, with a different interpretation, Tomboulis-Smolin. But, well, the difference is, of course, they never took the nth root of this expression. So, number one, of course, you never do such things in quantum field theory because it's a non-analytic, at the very least, it's a non-analytic function. So, and then secondly, of course, as you're saying, the formal path integral expression, of course, implicitly involves states, right, in whatever the states are. So what does it mean to take the square root? Usually, well, if that should have some fundamental status, you would say, okay, you go to the basis where whatever I'm sandwiching is a diagonal operator, and there the square root is well defined. But that's not what you're doing here. So I'm just wondering about the status of this nth root. Of course, in some of the cases, you consider kind of, this kind of drops out, but what is the status?
So I'm never taking the nth root of something like a ket. I'm always taking the nth root of a number that I've computed. In fact, that's why...
Of what?
I'm always taking the nth root of a number. I hope that was clear.
Yeah, that's clear, but what is the status of this? If one does it at the level of the transition amplitudes.
Oh, I don't think there is a status. We're deciding to change the rules of how you compute probabilities to invent a model which demonstrates a violation of quantum mechanics. And so I can't provide you an answer for your question in the context of quantum mechanics. Maybe I'm misunderstanding you, but I...
No, but okay, but you are picking up non-analytic behavior, so that has physical consequences typically.
If it does, and it's something that's observable, I would love if you could point that out to me so we could work it out and rule this out, because as far as I can tell, the predictions are very weak. But if there's something that's more drastic, then I'd like to know. But I personally haven't worked that out. So maybe we can talk offline if you have suggestions.
Okay. Next question.
Cool. All right. Thanks, Jordan, for a very clear talk. I feel like I understand what you guys are doing now. So I had a question and a comment. So for the first question, is it correct that all the post-Newtonian corrections would be unchanged by this setup? Because there was a kind of statement like throw out loops and...
Yeah, I knew you would ask.
You knew what to ask, perfect. Okay. So I'm asking, can LIGO rule this out, or are all the post-Newtonian classical corrections still maintained, despite the fact that you might think they look like loops?
Yeah, no, I knew you would ask. A little short backstory. We had worked out the no loops thing right before my first visit to Caltech in 2019, and that's when Cliff wrote with collaborators some of these incredible papers on post-Newtonian, post-Minkowskian corrections and graviton loops, pointed me to John Donohue's papers on graviton loops, and Philip and I went back and sat down and scratched our heads for months. But the kind of way out of this is that I mentioned that graviton loop stuff, I'm going to call it an aside, because that fact that you just mentioned confuses me very much. And I think the point is that in this theory, you can no longer make that extrapolation between correlation functions and potentials that you might do. And instead, what we need to focus on if we're talking about something like a macroscopic object is those propagators. Because we know in those propagators, we had the full semi-classical Einstein equation appearing. We know that those nonlinearities are in that equation. And so there seems to be some divide, which you don't see in conventional quantum mechanics, between particle propagators and correlation functions in a field theory. They're just not equivalent.
Because I think if you compare to like the usual Fokker-Lagrangian worldline or non-relativistic general relativity from Rothstein and Goldberger, it actually might be okay, because they're strictly all the loop diagrams they draw are actually truly quantum. But anyway, we could discuss offline. But a second comment I make is, now that I kind of understand the setup, so like in the privacy of my own home, I've thought about modifying quantum mechanics. And there's a way of modifying any quantum mechanical system such that the classical physics is the same, but the h-bar expansion is modified. And you get weird factors of like multiplicities of the action. I can tell you what we can talk with equations later, but the idea is basically you put a potential for h-bar. You let h-bar be dynamical, and when you look at the saddle point, you actually find that the classical physics is the same. So it gives you things like this s to the n, but I think it might be a generalization of this picture, which would be invisible to classical physics, like, but at least in terms of h-bar counting, but would be modified. So maybe we can talk offline about it.
I would love to talk about that. That sounds very related.
I had a short question and a longer one. So the first short question is that you got this V effective that you showed us somewhere, which somehow was truncated at a finite. It doesn't become minus infinity. It just gets a finite bound. Is that lower bound universal, or is it system dependent, or what?
That's a good question. I believe that was system dependent because, yeah, you can only go as deep as, how do I say this? The depth of that is basically determined by the number of ions in your extended body.
But how does it go? I mean, does it become?
Sorry?
Does the potential, the bottom of the potential become shallower and shallower if I have larger and larger system, or does it become deeper and deeper?
Deeper for larger systems.
Deeper for larger.
Yeah.
Okay. So then, and the larger just means n, or also has to do with mass of the system?
I was assuming, I guess, constant density, so
I see.
Same thing.
Okay. Okay. The more general question, I still don't get my head around the viewpoint. So I'm going to take not Philip's point of view, but and neither your point of view, but something in between, which Philip said that was he would have found that acceptable if he had done it. So the point of view that I would like to say is that the initial and the final state are just traditional kinematics, the Hilbert spaces. And in between, you wanted to have these replica Hilbert spaces, but you don't need that. I mean, I can just do a path integral. I don't need, Feynman didn't introduce Hilbert spaces in the middle. So we could just do that. So if we did this, then the statement would be, theory would be much more kind of, at least finite people like me would be understandable in the sense that one would say that these kinematics and what I'm modifying is really dynamical rule about the transition amplitude from here to here, but the interpretation of the translation amplitude, observations, etc., is the same as before, but I'm just changing the dynamics up here.
Maybe we should talk offline in some more detail, maybe with the blackboard, because if we could formulate it that way without introducing many different integrals, I think that would be preferable. This is what we landed on because we didn't exactly know how else to formulate many different paths interacting with one another without introducing multiple different integrals.
Right, no, multiple integrals would be fine. Okay, we should talk about it. Yeah. But we don't need Hilbert spaces. Okay. But my confusion about the basic approach, I don't see Philip's claim that this is a finite theory alternative to string theory or something like that, right? I don't see that at all, because it seems to me that somewhere there are so many approximations, and I just want to understand those approximations. So first of all, supposing I had a field theory, not particles, as in your talk, right? I mean, I had some field and that. So in that case, what approximation am I using to calculate the gravitational interaction between these fields? Am I just looking at linearized gravity and saying that these are stationary tensors and I'm just calculating linearized gravity to some approximation? Or to what, something or, yeah. In other words, if I'm doing, say, post-Newtonian or post-Minkowskian or something like that, where am I stopping?
I don't exactly understand the question, where are you stopping? But yes, it was done. Sorry. Yes, it was set up perturbatively, at least in the field theory part of this calculation. I was just doing conventional EFT expansions, but now I have these extra n parameters and extra flavors.
So you're stopping at order
around.
G, or if you're doing expansion in G, are you stopping at the first order in G, or?
In principle, no.
In principle, no.
I mean, I'm still assuming that this is a low energy EFT, and so it's only valid up to some scale. But in principle, one has to do the full expansion and say, okay, these are now subleading just because of the energies we're working at. I can truncate my approximation here. But I never said anything about UV completion. I pointed out that people had mentioned renormalizability in models that look like this, and that was more just to pique a little bit of interest, but I'm not going to claim that the CWL theory is a UV completion for quantum gravity.
Okay.